One of the topics you'll learn about at the end of a mechanics course like this is the idea of what torque is. Now, torque is kind of an interesting property here, and if you think of something like a force as causing linear motion, then what torque is going to cause, F is force, and this says linear motion here, what torque is going to cause is rotational motion. Because as we know, when you get to this part of the course now, there's linear motion where things move left and right and up and down. There's also rotational motion where things can say rotate, say clockwise or counterclockwise. So if F ultimately generates linear motion, torque is what's going to generate the rotational motion. And they have exactly analogous expressions because we know from some other analysis we did here that A is the sum of the forces divided by M. So the acceleration then comes from the forces, and acceleration, of course, is what drives motion. And likewise, we can say that angular acceleration is going to be the sum of the torques divided by I, where I is the moment of inertia of an object in there. So if we have A acceleration, we can expect motion to happen, and if we have angular acceleration, we can expect rotation to happen. So torque is sort of the focus of this particular video. What I wanted to do here was give you sort of an easier visual way of remembering what torque is and how it works. So what we'd like to do then is to develop a working equation for torque, something we can sort of use as we approach problems and discussions and things. And it'll go like this. I'll have a big blank here which will get filled in, but tau, that's the Greek symbol tau for torque, is equal to something, this big blank right here. And I'd like to go ahead and get it filled in. So the way I'm going to approach this particular tutorial here is I want you to think about what a door is and how a door works. A door sort of looks like this, of course. It's a big rectangular object like this, and it might look something like this, and there's a door handle right here. And there's some hinges over here, like here and here, that technically, in terms of this physics course, is the axis of rotation. So when you think about what it means to open and close a door, you're actually rotating the door about this axis, like you like to give the door some omega, some rotational velocity, so that it'll either open or close. So that's what the door looks like then. And my claim is that a very good visual for understanding what torque is just to think about what a door is and how a door works. So what I'll do then is I'm just going to scoot this thing over a little bit. And let's look at the door from the top. So if you imagine we're looking down on top of the door, we'd see the edge of the door like this, and we'd see the hinges right there. And this will be the axis of rotation right here. So let's try to remember that the door always rotates about that big dot there. That's the axis of rotation. So let's think about then what it means for us to open a door. Okay, so of course we have to come and push on the door, and so there's your first clue for you right there. Pushing on the door is going to be where our force comes from, because remember what forces are. Forces is what happens when you push or pull on something. That's definitely what an F is right there. So it turns out that yes, the torque is intimately related to an applied force somewhere. That's what's going to be part of what we write in this blank right here, part of our definition of what torque is right there. And let's just see how it works. So in the first example, I'll just use the most common sense that if I wanted to open up this door here, I would push on the door, say this way, with my hand. I'd give it a good push like that, right on the door handle, and I'd expect the door to swing open. So if I look at my top diagram right here, pushing like this would correspond to pushing on the door just like that. Okay, and there's my force right there. So now I want to ask then, how do you think the torque, and remember what torque is now, torque divided by the moment of inertia of the door, which we won't worry about right now, gives angular acceleration. And if I can give that door some angular acceleration, which again comes from the torque, then what I expect to happen to the door is I'd expect omega is equal to omega naught plus alpha delta t. I'd expect if the door had some angular acceleration that over time it would develop an angular velocity, and hence the door would start to rotate or the door would open. So back to the force here, we have to ask the question, how do you think torque then depends on force? What is the relationship between them? Do you think the larger force there is, the larger torque there's going to be, smaller force, smaller torque, or larger force, smaller torque? What combination do you think there is? Well, I think with common sense then we'd say, look, the harder I push on a door or the more force I have, the more angular acceleration I'm going to expect it to have, the quicker I'm going to expect it to start rotating. So I'm just going to say then that probably the larger the force, the larger the torque, and that would be correct. So the first thing that we'll write over here is that torque is going to be equal to force. Now there's going to be other terms here. Torque is not equal to torque, but we're building up this equation. So certainly force is going to be a player in there. And it turns out that torque is just proportional to force. It isn't force squared or force cubed or anything like that. Tau torque is just proportional to force. Okay, let's go on with it then. But that's not the only place I can push on the door. So the next thing I can do is I could also come over here and push on the door, say, at the halfway point. There's a lot of decorative doors, say in Europe and so on, where the door handle is right in the middle of the door, and I could push on it right there. The top view would look like this, pushing right here. Here's my other force here. So the question I'd have to ask then is like, how does the torque made by this force affect opening the door? Is it easier to open the door, harder to open the door? What's the situation going to be? Well, you could try this yourself, and even if you wanted to move in the most extreme case, just keep moving away from the door handle and try pushing on a door right here over the hinges, right there. Try pushing on it right there, which would correspond to pushing right here. So you have to look at this situation and go, okay, if I push way out here, the door opens pretty easily. If I push in the middle, it'll still open, but it's not the ideal place to push. It just doesn't feel like it. You really need to try this experiment in order to feel how this is going to work. But if I push on the door all the way over at the hinges, it doesn't open at all. So I am pushing on the door. I do have a force on here. I can push as hard as I want, but if I push right at the hinges, it doesn't open. As I start to move out, it does start to open, but it's easiest to open when I'm way over here at the edge. So the idea then is like, what else does torque depend on? Well, it turns out it depends on how far from the axis you push. So it certainly depends on, I'm going to call this parameter R here, and this R here is how far from the axis do you apply the force. So I have to introduce another parameter like this. So over here, this is the best way to open a door because I'm maximizing the distance between the hinge and the point of application of the force. There'd be like an R1 right there. That's a great way to open the door. The door will still open if I put my force at a distance R2. That'll still work. This R gets to be a little awkward in here because R is about 0 in there. So when I'm pushing right at the hinges, there is no distance between where I'm pushing the axis, so R is 0, where here R is maximum. Now it has nothing to do with the force, it's just purely the distance, the place where I choose to push on the door. So the next question then, how do you think torque depends on that distance? Do you think the farther from the axis of rotation, the more torque I get? Or the farther from the axis of rotation, the less torque I get? What's it going to be? Well, it turns out, I won't waste much of your bandwidth on this one right here, that it's also going to be proportional to this R in here. Torque is going to be proportional to R. So we just put that in there. This is kind of a thin marker. Let me make it go thicker like that. Just proportional to R. So it doesn't depend on R squared. That'd be impossible to just guess out of R cubed. But it turns out it's just proportional to R. So there we go. We have a nice working equation for torque. We're not quite done yet, but we can see that torque does depend on two things. How strong the force is that I push on the door, and how far from the axis of rotation do I apply that force. So there's one more little property in here that torque is critically dependent on. And let me erase some of these forces here so we can sort of get out of here. So we agree then that in order to open a door, you should push on the door just as hard as you can, and you should also make your distance as far from the axis of rotation as you can to get a nice big torque, which will lead to an angular acceleration alpha, which will lead to the door opening. Okay. How about this though? Suppose I sort of agreed then that the farther you push on the door, the farther from the axis of rotation you push on the door, the higher the torque's going to be. So I know I want to push on the door sort of in this area right here, or from the top, you sort of in this area right here. That seems to be the optimal position because I'm making R as large as possible. So I say, okay then, go up to the door and push on it, edge on like this. Push on it just like that. Top view, push on it just like that. With the largest force I can possibly muster. So you have to agree, everything we said so far holds. I'm applying a force to it, hopefully nice and strong. I'm as far from the axis of rotation as I can possibly get and still be on the door. But we know if you push on a door on the edge like this, it's not going to open. So there's a problem in there. I've satisfied the force, I've satisfied the R, the distance from the axis of rotation, but the door still doesn't open. So yes, it depends on the angle then. There's also an angular dependence for torque, which is something else to sort of grapple with. I'll sort of write it right here. Let's define the angle theta here as sort of the angle between F and R. That angle matters. So remember, R here is always sort of the line between the axis and the force. I'll call it the force point, if you will, the point of application of the force. That's always what R is right there, sort of a straight line. It doesn't always have to be in the material, but in this case it is. So, okay, R, the line between the axis and the force point. Well, here we go. Here's the axis right here, here's the force point. So this R is going to be this nice dark line here right in the door. On the actual door over here, here's the force, here's the axis rotation, there's the R right there. So there's always sort of an axis in there like that which has a direction. So what the issue is now is, well, what angle do you have between the force and that axis? And if I look at sort of this goofy case here where I'm pushing edge on the door, you can see here that the angle between the R, which say might be this way, and the force, this is a 180 degree angle. You can also sort of think about it as a 0 degree angle or anything like that, but it's just a particular type of angle. And what it seems to happen in the case like this here is these cases here don't seem to be generating any torques for some weird reason. Even though I'm far from the axis of rotation, I have a nice strong force on it, I'm not getting a torque. How come? Because the angle's wrong. And so you have to think now, well, what trigonometric function sort of gives 0 at 0 or 180, but gives a nice maximal or strong response when you push on the door properly, which is like this, the first purple force we had earlier in the video. This is the best force right here. This is the force that sort of makes things happen right there. So this is a 90-degree angle. So what trig function is sort of large at 90 degrees and small at 0 degrees? Well, I think very carefully, it's going to be the sine function right there, the sine of that angle. And so we're done. That's the working equation for torque. It depends on how hard your force is, how far you are from the axis rotation, and the angle that you choose to apply your force relative to the distance from the axis. And one more thing then, R, technically, if you go searching through your book and stuff like this parameter called R here is usually called the moment arm. So technically then, torque depends on the force, the moment arm, and the angle between the force and the moment arm.